Now that we have our non-specific binding test done and the buffers that we want to use with our sensor chemistry chosen, we'll then go on to our ligand immobilization step. Now, so this means that we're now ready to start our specific binding test, and the first step will be immobilizing our ligand to the sensor surface. So as mentioned earlier, for each sensor chemistry, you're going to want to reference the specific sensor chip tech guide for a step-by-step protocol. And also, while immobilizing your ligand, we have a very useful equation here that you can reference, which I have expanded in more detail here. Now, this equation is used to estimate the maximum theoretical analyte binding signal that you will obtain in an SPR test, and it's depicted here as the Rmax. Now, the units of our response signal are nanometers or picometers. As remember, we are tracking a wavelength position. And then we can relate the analyte binding signal intensity to the molecular weight ratio between the analyte and the ligand, as well as the ligand immobilization level. Now, this term, the ligand immobilization level, is determined experimentally by calculating the net shift in the response signal during our ligand immobilization step. And this is very well outlined in our sensor chip tech guide. Now, say for example, if the molecular weight of our analyte and ligand are about the same, this ratio will then be 1. And if we have 800 picometer of ligand immobilization, we should then expect our analyte binding signal to be at a maximum of 800 picometers. Now you can tell that this equation will become especially important if the molecular weight ratio is small. So say we have a large ligand on the surface and our analyte is a smaller molecule. Now, when this ratio is small, we are going to want to ensure that we have sufficient ligand immobilization to be able to detect the analyte binding signal. Now, for our response units, you're going to want to aim to have at least an Rmax of around 50 picometers to ensure that we have a good signal-to-noise ratio for detection. Now, knowing all this, we can have a minimum goal for our ligand immobilization level. So what we have here is an example of a ligand being immobilized to the carboxyl sensor in our 2-channel open SPR instrument. Now, as you can see from this response graph on the right, both channel 1, which is in red, and channel 2, which is in blue, are activated by the EDC NHS. Next, the ligand is then injected only into channel 2, which is followed by an increase in the response for the blue curve and a flat line for the response for channel 1, which is the red curve. And then after that, we're going to inject the blocking solution into both channels. Now this will result in channel 1 being our reference channel and channel 2 being our active channel. Now, as was done for the non-specific binding test, our reference channel may be either untreated, activated and then blocked, or prepared with an inactive protein to mimic the physical properties of our active surface. Now, one thing to note is if the ligand immobilization response doesn't reach that estimated level that you calculated for your Rmax, you should then perform a second or possibly even third ligand injection to get that response level high enough. It should be noted that you should not proceed to the analyte injections if the ligand immobilization level isn't sufficient to reach an Rmax of at least 50 picometers. Alright, so now once you have your ligand immobilized onto the sensor surface, you will now be able to work with your analyte injections. So as mentioned earlier, you're going to begin introducing your analyte to obtain your first binding curves. Now, if you remember during that part at the beginning of the session, you're going to need to obtain these binding curves at multiple analyte concentrations. Now, if an estimate of the KD is known, you're going to want to use a range of analyte concentrations between 0.1 times and 10 times the KD value. If no information is known for the KD, it's recommended to start at a low nanomolar analyte concentration and increase this until a response is detected in the instrument. You'll also want to be using between 3 to 5 analyte concentrations for your analyte injections. And you're going to want to dilute your samples using either a 2- or 3-fold serial dilution so that you can obtain ideal spacing between your different binding curves. Now, one of the most important things to remember is that you want to ensure that the analyte sample buffer and the running buffer match as identically as possible. Ideally, they should be identical with the exception that one has your analyte sample in it and one doesn't. And to do this, you should be using your running buffer to either directly solubilize or directly dilute your analyte samples. And as mentioned earlier, between each analyte injection, a regeneration solution may be necessary to ensure that we have the same number of ligand binding sites for each analyte concentration. And we're going to talk about this in more detail right now. So again, as I just said, before you start to collect your next analyte binding curve, you may need to use a regeneration solution to remove your analyte from your ligand because you want to ensure the same number of ligand binding sites are available for each analyte concentration that you are sampling. Now this regeneration solution, what it's going to be doing is it's going to be disrupting the binding of your analyte to the ligand, causing the analyte to be fully removed from the sensor surface. Now, if for instance your interaction has a very fast off rate and all of your analyte will dissociate on its own within 2 to 10 minutes, then all you'll need to do after your analyte injection is wait for the analyte to come off, and then you can proceed to the next analyte injection without the use of a regeneration solution. Now, however, if this dissociation rate is slow, it's not very practical to wait until it all naturally dissociates. In this situation, you're going to be using that regeneration solution to disrupt your ligand and analyte binding. Now, this regeneration condition is going to be completely dependent on the binding mechanism of your system. Now, to determine these optimum conditions, you're going to be introducing your analyte at a fairly high concentration that'll slightly saturate your ligand, and then you're going to screen for the optimum solution for your particular binding partners using a regeneration scouting procedure. Now, this can be done by trying out a variety of different solutions, which include either acidic, or basic, or ionic, or detergent. Now, as a general rule of thumb, you're going to want to start with the least, or you're going to want to find the least harsh condition that can get the job done. Because ultimately, this regeneration step is going to be shocking your ligand, and you don't want to damage it or alter its binding capacity thereafter. This regeneration condition is also recommended to be run at a faster flow rate to minimize the exposure time and any potential damage that may happen to the ligand. Now, as mentioned earlier for the non-specific binding conditions, the literature is a great resource for selecting your regeneration step, because if a similar system to yours has been studied with SPR, because this is completely dependent on your binding partners and not the SPR instrument, those conditions should also work to regenerate this binding system. If a regeneration step is needed, once the optimum regeneration solution is found, it is recommended to precondition your ligand with this solution prior to your first analyte injection. This will ensure the highest consistency throughout your test. So for example, in this response graph below, our first step here is the immobilization of our histidine tag protein to our MTA sensor. And as you can see, there's a slight off rate that's occurring after this step is done. Next, we're going to precondition this ligand on the sensor with our regeneration condition. And you can see that some of the loosely bound ligand has been removed from the sensor surface. And this is stuff that probably wasn't captured via a histidine tag and was loosely interacting with the sensor surface. And after this, all of our subsequent analyte and regeneration steps all return to the same baseline, suggesting that we have a highly consistent test. Now, one thing to note with this is that our regeneration solution is going to cause a bulk shift, as this solution will differ from your running buffer, which will cause that buffer mismatch. And this is completely normal. We have now discussed the 4 main areas in the experiment that may require some optimization for your binding system. The first area we looked at was the non-specific binding. And this will involve optimizing your running buffer with different additives. The second area would be the ligand immobilization step, and this will be specific to the sensor chemistry that you are using for your binding system, and you may need to optimize this step to obtain a desired immobilization level. The third area that might need some optimization is your analyte concentration range, and as stated earlier, this is going to vary for each binding system. In general, you'll need to use a concentration range that's around your expected KD value for your interaction. And the final part of the experiment that may need optimization is your regeneration solution. And again, this is going to be completely dependent on the samples that you are analyzing.